Okay, we're gonna continue on with chapter 5. Last video was the wave-like characteristics of light, and then we showed this relationship between wavelength and frequency, and it was the double slit experiment that showed this wave-like behavior of light. So we said last time that light has wave-like and particle-like behaviors. So here's how experimentally they got the particle-like behavior portion of it. So they had the wave-like, and they had experiments around the same time that Einstein was able to use to figure out the particle-like. So the experiment was a photoelectric effect. And the photoelectric effect was, and this was done way before they were actually able to, Einstein was actually able to summarize his assumptions. So they shined light on a metal surface. And when they shined light of a high enough frequency onto that metal surface, electrons got emitted or ejected off of the surface. So it wasn't like any frequency light that could come in. It had to be high enough frequency light to hit that metal surface, and it depended on the metal that it was, to hit that metal surface and eject an electron from it. So based on the fact that it was a certain frequency of light that had to be high enough, or nothing happened if that frequency wasn't high enough, Einstein made this assumption that when the light hit and ejected off an electron, that light was acting like a stream of particles. And that stream of particles we now term photons. So that's the particle-like behavior. Photons aren't a particle, they're what we call a quantum of energy, like a tiny packet of energy. So that's why we call it particle-like and wave-like. So in the next video, I'm going to show you a relationship that shows not just that light has wave-like and particle-like behavior, but all matter, including electrons, which is what we're going to study, has the wave-like and particle-like behavior. So after the photoelectric effect, and Einstein sort of made his assumptions about the particle-like behavior, then came along Max Planck. He used all the experimental evidence that was available at that time to relate the frequency of light to the energy of light. So he saw that relationship when there was a certain threshold frequency going on to that metal surface with the photoelectric effect, that might have something to do with certain energies. So the equation that he came up with, and he got a constant named after him, is this relationship between frequency, which again, that's not a V, that's the Greek symbol nu, the frequency of the light and the energy of the light. And then they're proportional, but he still had to have this proportionality constant in there, and then he named that after himself. So that's Planck's constant that's in there, which has a set value based on the units that you use. So if you look at what he put here for light, the higher the frequency of light, the higher energy that light has. So they're directly proportional. So if frequency gets higher, energy is higher. If frequency gets lower, that's lower energy photons or light. So if we take this particle-like representation, and what we had back on the video with the wave-like relationship between these, and we talked about the relationship between the wavelength and the frequency here, we can combine both of those to get this sort of equation that relates other variables. So it's still the same ones, but we don't have a relationship over here or here where we can relate the energy to the wavelength of the light. But through the frequency being in both of these equations, we can combine those two equations to have a different combination of variables. So here you have Planck's constant, speed of light, which is a constant. So the top part is all just constants. And then there's a relationship through those constants between energy and wavelength. So these are inversely proportional. So the higher, let's say the longer the wavelength. So if this is longer, think about it being bigger. So the longer the wavelength, the smaller the energy. So we'll say lower energy. So like when we talked about the electromagnetic spectrum, we had long wavelengths down by microwaves and radio waves. So those longer wavelengths had lower energies associated with them. And then you think about all the other way, there was gamma rays. So those gamma rays had really short wavelengths, and those short wavelengths would have really high energy. And you think about that with X-rays or gamma rays, you don't want them going into your body. So you think about those having high energy, and the reason they can penetrate into your body is because it's the high energy light. So we talked about that we had the wave-like behavior, and we had the wavelength and the frequency related. Then we talked about particle-like behavior, and we related the energy and the frequency. And then we sort of put them all together. But all of this still just talks about light. Our ultimate goal was to figure out where the electrons are. So we figure out where the electrons are, we can talk about our chemical reactions again. So this last part finally relates all this information that we learned about light and realize that we can say the same things about electrons. And here's why. So DeBroglie came up with an equation that we're going to show, which is ultimately combining all of these. Ask the question, could all matter, which electrons are, so anything that has mass and takes up space, have wave-like and particle-like behavior, just like the light did. So the light was particle-like. It was like a particle because it's massless. But we know matter has mass, but you can't imagine that everything around us has wave-like behavior too. Seems not possible, or not observable, definitely. So we look at the equations that were available at that time for DeBroglie. We already saw this relationship that we came up with combining our two equations into one equation. So we had the energy related to the wavelength, and then these constants. Everybody knows Einstein's equation. You've heard it at some point. E equals mc squared. So that's energy, that's mass. C is still the same thing. C is the speed of light. So since these relationships both equal energy, that must mean that they equal each other. So I wrote that over here, so you can see that hc over lambda equals mc squared. And then you can solve that for lambda. So we're just doing algebra here, solving for lambda. When you get over here and you've substituted and done the algebra, one of these cancels out, just algebraically, and we end up with the lambda equals the ratio of these constants, and then that's mass. So let's write that down here. We're in our room. So that's mass. This we talked about before is speed, but it's the speed of light, which is fine because we've been talking about light. But DeBroglie's hypothesis, which ended up the DeBroglie equation, was, he said, if I'm going to make this relatable not to light, but to matter, then I need speed. So speed's like velocity. That's a V, not a nu. So if he put V in where the C is, because they're both a speed, then you could have the wavelength has h, which is Planck's constant, over mass, and instead of putting in the speed of light, because we're going to talk about it in terms of all matter, we put v. So v for velocity. So we can look at now the relationship between matter that has a mass and wavelength. So if you get really large objects, which are like the observables that we can see with the naked eye, then you can see like, oh, it would be hard to see for things that are really big because the wavelengths would be really small. So for things that are big, you wouldn't even see that it has wave-like behavior because the wavelength is so small, it's almost like infinitesimally small to the human eye. But that's the relationship that we can use to go back and talk about electrons and ultimately quantum mechanics, because when we talk about electrons, we have to say that it has that wave-like and particle-like behavior. And also, in the book, there's an experiment that shows electrons and how they can have the same wave pattern experimentally that they determined way after they did the double slit experiment. But it shows the wave behavior of electrons. So they experimentally, not just calculation-wise, showed that they have the wave-like behavior. And particle-like, they are particles.